So, right then, we need to talk about a mole. And we've already talked about a mole. And each semester I'm a little bit different with regard to how creative I am. I don't know. I think I'll just let the slides speak for themselves. But we talked about, by definition, let's see, the carbon-12, one atom of carbon-12 weighs exactly 12 AMUs. That's kind of the definition of an atomic mass unit based upon that isotopic form of carbon. If you have exactly 12 grams of carbon-12, then you have a mole of carbon-12 atoms. And you can do all sorts of kind of interesting factor label problems from there. Basically, all of that's where a concept of a mole is. Now, I posted on Twitter because I went out there and I said, how come they call it a mole? And I don't know, it has to do with scientists in Germany, and it was first actually linked to the number of gas particles, and you're familiar with the standard temperature and pressure of gases and the standard volume, and I don't know. But the mole, M-O-L-E, actually came from kind of grouping of molecules. So now, of course, we can apply the concept of mole to atoms and molecules and hockey pucks and rice grains. Okay, basically, if you have 6.022 times 10 to the 23rd of anything, you have a mole of those things. And as I was stumbling today on the internet, this actually is a rounded number. This is 4 sig figs. There are actually some more digits beyond that. So, yeah, it does introduce uncertainty into your problem if you go with a coefficient of 6.022. Yeah, it's affectionately called Avogadro's number. I always think of avocado, Avogadro, yes. And we all decided that on October 23rd, on 10/23 at 6:22 in the morning, or so, I don't know. We're all just supposed to celebrate.
So before I mentioned that avocado thing I think it was like last week, you had actually thought of that too?
Oh, yeah.
Okay.
I think the word avocado a lot with Avogadro. Yes.
In Portuguese, avogada is thank you for female, and avogado is male. And it makes me think of that for some reason.
But it's thank you, you mean?
It's thank you.
Oh,
They
okay.
have male, female, thank you.
Very good.
It's kind of similar.
Well, Avogadro was the last name of, and I don't know what nationality he was, but of a scientist. So.
There's a lot of French, Chinese, Italian, kind of a melting pot where I was, and so it would be surprising to hear that.
Interesting. I love it. That's so cool. Very cool. And then I think I laughed that this is one of my favorite abbreviations. You get to drop the E, right? Instead of like M-O-L-E, it's M-O-L. Okay, that works. Okay. So a mole is 6.022 times 10 to the 23rd. Now that's a big honking number. So basically take the decimal right here and move it this way 23 places and fill in zeros. You know, it's a big number. So,
Just count.
right, exactly. A dozen is 12, a gross is 144, and a mole is 6.022 times 10 to the 23rd of anything. Definitely could lose count. So I've got some, I brought some rice grains in here. So if you have a mole of rice grains, which this is not a mole of rice grains, so nobody panic. So, but this is 10, I just counted 10. And then I scaled up from 10 based upon the mass of this. Then this is about 1,000. Oops, I didn't count these. These are about 1,000. Okay. And then the rest of the bag, which I've lost a few, but this is 2 times 10 to the 4th. Okay. So what? 4,000, or excuse me, this is 2,000. This is 1,000, not 10,000. This is 1,000. Doesn't quite look right.
20,000, right?
20,000, thank you. Much better, 20,000. And in terms of a mole, This is 3.3 times 10 to the minus 20th. So this is just a fraction of a mole of rice grains. So anyway, if you had a mole of rice grains, they would cover up the land area of our planet, and we'd be covered up to a depth of 75 meters.
Wow.
Yep. Thou shalt not have that many rice grains. Yep.
Oh, why?
But there have not been that many rice grains, a mole of rice grains, that have been grown since the beginning of time. Okay? Even though it's a staple in a lot of cultures, rice is. Okay? So if you want to segregate a mole of rice grains, it would fill a cube 120 miles on all sides. And send that evil rice grain into outer space, right? So switching gears to marshmallows. So I just think of the Stay Puft Marshmallow. Don't think of anything. Clear your mind. Clear your mind. And the guy, yeah. So a mole of marshmallows would cover our country up to 600 miles. Some people would be in heaven, but that's a lot of. Okay, so 600 miles deep. Suffocate, yes. We die happy. Snowflakes, okay, so think of like Iowa, the whole snow thing. They're beautiful, but if you had a mole of snowflakes, they would cover the United States up to a depth of about 2/3 of a mile. Now, if you're like me, you're like, now, Mrs. Snipes, we know that snow is not so. Some is packed in, some is light and fluffy. Just
That
pick.
was Rhonda.
Yeah, that's true.
She liked that thought.
Okay, so you said you'd lose track if you were counting a mole, okay? Well, you could task everybody on Earth with counting a mole, okay? Okay, we're going to count a mole and we're going to add them all together, all of our counts together. Well, you would need, at the time this was written, about 51,000 times the number of people on one Earth. So you need that many people, and it would take us 75 years to do it. Stop. Talk about needing a life, right? So sometimes when you take programming, this is what was for me, for whatever language, just a couple languages, I guess, I used to know. And they basically tell your computer to count. You're like, the computer must be so bored. Well, if you have a fast computer that counts at a speed of 1,000 millions of instructions per second, pretty fast at the time this was written, and you task your computer with counting, doing the number of iterations, the same number as people in the United States. At the time this was written, it would go ahead and do that number of iterations in less than a second. But that same computer, if you want them to count a mole, okay, it would take 1.9 million years to go ahead and do that many cycles. You're like, dude, it's just a big number. Okay, hockey pucks. If you gathered a mole of hockey pucks together, they would equal the mass of the moon. Kind of strange. Basketballs, the volume of a mole of basketballs would be the same as the volume of the Earth. Kind of an interesting thought. This is one of my favorite. If you're like me, you just like diss the whole penny thing, unless it's heads up, and then I might pick it up. But then you're like, I should leave it because somebody else might need it worse than me. So anyway, so if we had a mole of pennies, and at the time this was written, we're going to give everybody on Earth their fair share. Their fair share would be 1.5 times 10 to the 14th pennies. You're like, what's in a penny? Well, that means dollar-wise, that's 1.5 times 10 to the 12th dollars, right? Does that make sense? Well, that's a lot of money, right? So this says that people could go ahead and spend their money at $1 million a day, and they could do that for 4,000 years if they'd live that long. Of course, they wouldn't. But a mole of pennies would be a bad and evil thing. It's like I Dream of Jeannie, where he used to ask for the strangest things and things that you probably don't really want. So if you wish for a mole of pennies, you better take it back, because it would cover the land area of the Earth, 420 meters. Yep. Okay. But The reason we have this big number, this large counted quantity, is basically because atoms and molecules are so darn small. So if you have a mole of atoms, it's something you can sink your teeth into. Okay, I didn't bring. I don't have water here, but if you were to have, picture my thumb is hollow basically, and we can kind of fill it with any sort of liquid. If you were to, it's about 18. Bless you, about 18 milliliters. 10, or maybe, I don't know. But 18 milliliters of water, about 18 milliliters of water, that's a mole of water molecules. So we'll be talking about that. So from any equivalency statement, we get two conversion factors, okay? And we're going to look at how we can use it as a conversion factor first. So we could say that, and we're going to start with atoms, we could say 1 mole of atoms, 1 mole of atoms over 6.022 times 10 to the 23rd atoms, or the inverse is another great conversion factor we could use. And we're going to know which one to use in our problem depending upon what units need to cancel and what units we're going to be left with. That's it. Okay, so 1 mole of atoms is equal to 6.022 times 10 to the 23rd atoms. So we're going to work a couple problems here. This first one's kind of weird, okay, where it says 1 trillion hydrogen atoms, okay. I think we're going to go with no uncertainty there, I think, if I remember how I worked the problem. So we're going to say if we have 1 trillion hydrogen atoms, how many moles is that? And then we're going to say if we have 0.55 moles of any atoms, how many atoms do we have, basically? Now you see a few things in brackets here, my brackets of atoms here and of atoms here. The things in brackets for these first couple of problems on this topic, brackets, that phrase of atoms doesn't have to be there. When we get rolling, basically, I will just simply say, how many moles is 1 trillion hydrogen atoms? How many atoms is 0.55 moles? Okay. So that's just, those won't be there. They're kind of optional. Right, so let's work the first one. And we're going to, that's the 1 trillion hydrogen atoms. We're going to go with no uncertainty in that number. So we're trying to go from hydrogen atoms to moles. So we're going to put the 1 trillion hydrogen atoms. For me, I probably would put 1 times 10 to the 12th hydrogen atoms just because it just looks so naked right there. 1 times 10 to the 12th hydrogen atoms. So now what's the next term going to be?
1 mole over 6.022 times 10 to the 23rd atom.
Yep, exactly. 1 mole over 6.022 times 10 to the 23rd atoms. Perfect. Yep. So my atoms or hydrogen atoms, it really doesn't matter in this case because we only have 1 element. They cancel, we have moles of hydrogen atoms. So if you have your calculator, why don't you go ahead and kind of punch it in, make sure we're doing okay with scientific notation.
So we would go 4 sig figs on this answer?
Yep. I'd go with 4 sig figs, yep. Is that what you guys got? I got 1.661 times 10 to the minus 12. I see one head shaking, yes. 2. How we doing? A little number. Didn't work for you.
I can't remember how to
My exponential power thing.
I would.
Razor lowering it with it.
So I like yours is good. So I would go. I'll go 1 e and 12. divided by 6.022 EE, 23.
Did you guys get a free test?
Did you get that answer?
I couldn't remember the E. I was like,
Mhm.
what is that? Thank you.
Yes, good job. Did yours work?
It goes, so 1 times 12 divided by 6.022 10 to the 23rd.
Yeah. Should work.
Again, 1.661 10 to the 34th.
Let's see, well, this looked fine. Do that again. Slow-mo. He's got a times 10 to the x cubed. Wait,
That's what I was using. It was 10.
Yeah, you're using.
is that what the year key is
Yeah,
too?
that's what I'm using. That's weird. Well, you could just do a longhand and you come up with.
No, don't do it longhand. You might need to use, you might use parentheses.
Okay.
So try it with parentheses.
Okay.
Got me curious.
There we go.
Yep,
So just gotta make sure to put parentheses around it.
yep. Guess so. Okay, next one. All right, now this one's the mole to number of atoms. So we'll put 0.550 moles over 1, and then what does the next term look like?
6.022 moles, or the atoms are.
Yes, 6.022 times 10 to the 23rd atoms over 1 mole. Perfect. And then moles cancel. We're left with units of atoms. Get that?
I wouldn't want too many sig figs, but yes.
Okay. Yep. So we're going to go with 3 significant figures because that's what we're limited in the term 0.555. So yours has everybody's, these newfangled things. Oh yeah, okay. So yours is right there. So if you just go 0.555 times, and then for Avogadro's number, 6.022, and then hit that EE key, and then it gave you those, and do 2, 3, and then equals. That, and then it went ahead, and that's your coefficient, and that's times 10 raised to the 23rd power.
Thank you.
Perfect.
On the last two that I was calculating, I'm getting to the 24.
Yeah, it sounds like, are you sure you're using the EE key?
I'm using the EE key, but it doesn't mean I'm using it correctly.
Well, let me watch you do this one. No, nope, don't do the times. So you do 6.022 and then hit the EE key. Yep.
No times.
No, that does the time. Your time's there.
Okay, and then EE.
Then the coefficient. No, then the coefficient. And then EE, and then the exponent of 10.
10, do I put 10?
23rd. See how
Put
it's.
23?
Yeah, the zeros are ready for your 23.
Okay, it already acknowledges that.
Mm-hmm.
Okay.
So the way,
And then, that's what I'm doing. I was just doing a function.
an extra times.
Mm-hmm.
Very good. All right. So you guys don't have this slide, do you?
No.
Okay, won't worry about it. All right. Each match is a little bit different, so. Okay, so those were moles to atoms. That was the last one, and the first one was an atoms to moles problem. Okay? Now we're going to take it up a notch, and actually we're going to go from mass to moles and moles to mass. So there's this concept of called molar mass. Okay? So molar mass just means if you get 1 mole of anything, what does it weigh? That's molar mass. That's it. The mass of 1 mole. That's totally it. So units of molar mass are grams per 1 mole. So if we wanted to kind of unpack the molar mass, grams per mole, we'd say grams per 1 mole. Okay? Or we could say grams, units of grams, moles to the -1. So we're just focusing not on compounds, we're just focusing on elements so far. So if we want to just focus on the elements, the molar mass for any element is that decimal number, just like we talked about yesterday in lab. The molar mass is numerically equivalent to the decimal number is also the average atomic weight. So the decimal number counts twice. It's the average atomic weight for that element in AMUs. It's also the grams per mole. It's the molar mass for that element. It's the grams you need to set aside in order to get 1 mole of atoms of that type of element. Molar mass. So it's both of those. So for you visual people, I've got some moles, or your textbook has some, this figure has some moles set aside. So this is, each one of these is a mole. Copper, that's copper atoms. That's 1 mole of copper atoms. That's 1 mole of sulfur atoms. That's 1 mole of liquid mercury atoms. And this is 1 mole of helium atoms. So you see we have some are more compact than others, right? But if we were to count those atoms of each of those pure substances, we'd get 1 mole. So mole of sulfur, mole of magnesium, mole of tin, mole of silicon, mole of copper. So we actually, if these all represent 1 mole, the way this works then, we could go back and use the periodic table. You can find copper on the periodic table. Copper is atomic number 29. The decimal number for copper is 63.546. So if that's 1 mole of copper atoms, we know that the mass is 63.546 grams equals 1 mole for copper. See how that works? What's the symbol for tin? And I think that's one you're supposed to memorize. It's a weird one. SN, very good. So we find tin on the periodic table. It's right here. So it's atomic number 50. It has 50 protons in each nuclei. Okay? But its decimal number, its average atomic weight is 118.710. 118.710. Okay, so that decimal number serves as its average atomic weight, and it's also its grams per 1 mole of tin atoms. So that's how that works. So molar mass, if you have a periodic table, you got it for the elements. For each element, you know the molar mass for that element. And it's different for each element, right? Cool. Well, molar mass is great, grams per mole. That's what the units of molar mass are. We can actually go from grams to moles, or we can go from moles to grams. We can use it as a physical property of anything, and we could use it to go back and forth between mass and moles and mass. So here we go. Let's work a couple problems. So now this does depend on which element you have a question about. So right now we're focusing on calcium. And again, the thing in the brackets as we get started here won't be there. So it simply will say how many moles is 0.487 grams of calcium. That's exactly what I'll say. How many moles is 0.487 grams of calcium? So we're going to go from grams to moles. Well, if you have a periodic table, which you will always have a periodic table, you will see the decimal number for calcium is 40.08. So that's the molar mass for calcium. 40.08 grams of calcium per 1 mole of calcium atoms, or simply per 1 mole of calcium. It's a physical property of calcium. Notice the next box, all I did was I flipped it. I could also say, I could put 1 mole calcium in the top and 40.08 grams of calcium in the bottom. Or I could flatten it out. Just kind of, it's kind of what your preference is. It's a physical property of calcium. So let's go ahead and work this problem. So consistent with what I usually do, I'm going to hold this property as my second term. So what's the first term going to be?
487 grams.
Yep, 0.487 grams. Now, in my answer key, I went ahead and added, I'm working with calcium. You wouldn't necessarily have to if you only have one element. But I'm going to do it to be a little more explicit. So 0.487 grams calcium over 1. So I want my units of grams to cancel and be left with units of moles. So what, from the previous slide, what ratio goes there?
1/40.08 grams calcium.
Mm-hmm. 1 mole in the top and 40.08 grams in the bottom. Again, you wouldn't have to be explicit if you didn't want to, because it's just one element. If you had more than one element, you'd have to say which element you're dealing with. Cool. Now, is there uncertainty, is this exact, or is there uncertainty in this grams that we're dealing with? How many people think it's exact? How many people think there's uncertainty? I do too. So actually, that's going to help drive how we round it. How many sig figs are there? 3. Here's one for you. Are my decimal numbers up there? In this case, the molar masses of the elements or the average atomic weight. How many people think that those are exact? They are not. There's uncertainty there too. So how many sig figs do we have there? 4. Yep.
Because why?
Well,
What'd you say?
these numbers, these decimal numbers from the periodic table that we're using for molar masses, there's uncertainty in all of those. There's wiggle, there's play.
We're gonna take this one, because we're multiple.
Yes, and we're going to go with 3 sig figs. Yep. You got it. So did you get this? 0.0123 units would be moles, or moles of calcium.
122.
Had me a mistake.
0.0122.
Yeah.
Okay, sounds like that's the consensus. 40.08. Yep, very good.
So when we're writing out how many moles,
Thank you.
you don't want to put that in scientific notation, you want to put that as just a decimal.
You could put it in scientific notation. What would it be in scientific notation?
1.122 times 10 to the second. Negative second, yeah.
Mm-hmm. Yep, either one of those are great. Yeah, either one are great.
I was just wondering how you wanted us to write them out. Does it matter?
It doesn't matter, whichever you're more convenient with. Mm-hmm. Thank you, very good. All right, let's work another problem. So that was a mass to moles. This is a moles to mass. And again, the thing in brackets probably won't be there. So what mass is 1.33 grams of boron? Well, we're going to need to look at the periodic table for boron. And we're going to see that the decimal number is 10.81. And for molar mass, that means 10.81 grams of boron per 1 mole of boron. The inverse is great, and so is the flattened out version. So that's all about boron, physical property of boron. So to work this, what would the first term be? The first term is going to be the thing we want to convert, 1.33 moles or 1.33 moles boron, either way. So I want moles of boron to cancel, and I want to be left with grams. So what does that look like now?
What was the 1.33? Where did that come from? The periodic table?
The original problem. So what's that term, sorry?
1 over 10.81.
1 over 10.1.
Is there a folder in here?
There is a
Is it Evans?
handout thing.
No.
Is it?
Nope.
Okay.
You misplaced it. Sorry.
Okay. Oh, I heard you. Yeah. So you're fine. So you want moles to cancel and be left with grams. So what does that look like?
10.81 grams of boron.
Yes. 10.81 grams over 1 mole. Perfect. So moles will cancel. We're left with grams or grams of boron.
I can't believe she walked right into it.
What's that? So, is there any uncertainty in the 1.33? Yes. 3 sig figs. Is there any uncertainty in the 10.81? Yes. There's 4 sig figs, so we need to, of course, round to 3. So did you get this? Okay, we're all good. 14.4 grams. Sometimes students will say, well, do I multiply or divide? And I'm like, I don't know. I have to just kind of set it up and see. It's all multiplying to me, I think. But any questions about that? So these seem pretty straightforward, but these won't be. So let's take a look at these right quick. And we're not going to go on to the next part. While I'm thinking of it, just so we're all on the same page, we have one more part in Unit 1. It's about elements, and the elements, but the periodic table. So we'll be talking about the kind of how the periodic table is laid out a little bit on Monday. We should be able to finish up that last part for Unit 1 lecture on Monday. So that means, and I do this a lot, and you're like, oh, really? So that means on Wednesday, actually, I will start Unit 2 lecture material, which I think it's good because it gives you a few days to have Unit 1 lecture under your belt. So basically, we'll finish Unit 1 lecture on Monday, begin Unit 2 lecture on Wednesday, and have your Unit 1 exam on Thursday. Okay? Any questions? Wednesday we do, sometimes students will ask, well, Wednesday are we still set to go ahead and have one of those sessions over in the library? Who wants to show up and bring pizza? No. I don't think you can bring pizza for the library, but the answer is yes. So that will be after class on Wednesday. Okay, so let's take a look at these.
Good pizza in the shelter house.
Oh, that's true.
Yeah, pizza in the cafeteria.
Yeah. Yes, there's a cafeteria here. Those are great ideas. We'll have to kind of think along those lines. Let's see, that one's not there, so hopefully it's in this one. I looked at it in my office. So, patience. Well, it must have been back where I looked the first time. I need to merge these two.
You mentioned having some blank periodic tables.
So a blank periodic table.
Was that you who mentioned that?
Yes, for your unit exam, I will give you a black and white copy basically of this one. Yeah.
Did you have any ones to practice on?
I will try to remember to bring those on Monday. Because that Monday's a good one because we'll be talking about the periodic table, so I think I will.
For the unit one exam, I'll have to fill out a blank periodic table.
No.
That's rough.
Yeah. Oh my
Now,
gosh.
if it is the final exam, that would make sense, but
Don't give her any ideas.
I'll be the underdog in class.
Oh. Drat, I know I looked at it. It's 2:57. There it is. Goodness gracious. All right. Okay, so these are just stuff that we've talked about. The first bit we talked about today, we talked about how to go from atoms to moles and moles to atoms. And then we talked about how to use molar mass to go back and forth between mass and moles. So these kind of do an assortment of that. So like for instance, and some of you guys really totally don't need this hints. Like here's a hint for 57A. Use the molar mass of zinc to go from grams to moles, okay? Think you guys will be fine there. For B, whenever it says the number of atoms, you probably count on using Avogadro's number, and actually you will for B. For B, you're going to have to use both things that we talked about. Because notice you're going from a mass of chromium to the number of chromium atoms. So I kind of showed you down here, mass is given in kilograms. Again, a lot of you won't need these hints, but I'm going to put them out there on Twitter. Go from kilograms to grams of chromium, then use the molar mass of chromium to get to moles of chromium, and then use Avogadro's number to get from moles to chromium atoms. That's just it, okay? They're fun. They're all fun until someone gets hurt. No. So for C, I kind of got C. It looks like we are given so many gold atoms, and we're trying to get to mass. And so we'll go from the number of gold atoms to moles using Avogadro's number, and then the molar mass to get from moles to grams. And let's see, for D, there's probably a couple ways to work it. D's a hard one to sink your teeth into. Basically, you're supposed to say, what is the mass of one fluorine atom? So this is how I did it. I basically said, well, how many moles is one fluorine atom? So I used Avogadro's number to get to moles that you have, if you have just one fluorine atom, and then I used the molar mass to go from moles to grams. So probably a couple different ways to use that. And then 58A is similar to 57B. Okay, so for 58B, it's kind of something different. The capital M means molar mass. And so for this one right here, you're supposed to come up with the molar mass for this element. Now they've gone out and they tell you, I know that 209 grams, okay, is the mass of 2.80 times 10 to the 22nd of these atoms. Okay, so you're supposed to come up with the molar mass, which is grams per mole instead of grams per atom. So you're almost there. The only next thing you need to do is convert from atoms to moles in the bottom using Avogadro's number. Okay, so that's your hint for that one. This is one of my least favorite, number C. It drives me nuts. Basically, we have two elements, and you're supposed to say, what is the mass of a sample of phosphorus that contains the sum number of atoms of that atom has, that magnesium would have if you have 44.75 grams of magnesium. It just kind of drives me nuts. So basically, you're going to have to go from this mass of magnesium to moles of magnesium using the molar mass of magnesium. I love saying that. And then once you have those moles, set those moles equal to the same number of moles of phosphorus. And then if you have those moles of phosphorus, what mass would that be? So then you're switching now to the element phosphorus, the molar mass of phosphorus. So that's my hint for that one. Then on this one, we're dealing with a mixture. Sterling silver actually is 92.5% silver, and you're supposed to come up with how many copper atoms would you have if you have 33.24 grams of the mixture. So this actually brings into another skill that we talked about, where if you're focusing on the copper, of course that means 7.5% copper, you're going to have to use that as a ratio to get what mass of copper would you have in that mass of sterling silver. And then from there, once you have that mass of copper, it's not too bad to go ahead and use the molar mass of copper to get to moles, and then Avogadro's number to get to number of copper atoms. Similar for the next one, dealing with another mixture. Kind of similar. And then last but not least, or was that last? I guess that is the last one. Okay, so those are hints I'll push on out there.
Speaking of which, I signed up a Twitter account, and when I go on it, I don't see any of our school stuff. Does it have to do with being on a phone versus the computer?
The Twitter account, so then what you need to do is follow this account. So you need to, in a search bar in your account, say search for EA Snipes _ CHM165.
Well, I
And then
did
it should
that,
bring it up.
but all that's coming up are like, not this stuff, just other stuff.
Yeah, I'll have to, if you have it on your phone, I can look, it should come
I
up.
just signed up for Twitter, like, I don't even have a Twitter account, I was able to follow you.
Oh,
I wanted to be able to have it on my phone, like, because I'm on my phone more than
Oh, no.
at home on a laptop. And so I can see this stuff on my laptop at home. So I signed up for the Twitter